So let's start with differentiation. What is differentiation? Well, part of it is let's look at the language. If something is different, we're looking at the difference, the change in something, given a change in something else. So if we imagine this is our function, f of x, and we put something in here, and it goes through this, and it comes out the other end here as something else. Okay, that's our function. But just imagine if we change this function a little bit, say h plus h, or we could have x minus h if we wanted to, and we put that in, and then we work out, okay, what's come out the other end given this tiny change that we've made. And it's going to be some difference. It's not going to be the same as what we put in. That's kind of the nuts and bolts of differentiation. It's incredibly powerful. It's really, really important that you sort of get your mind around this concept, where we're not looking at how something is, we're looking at how it changes, how something changes, gets older over time, how it speeds up or slows down, how it changes direction. It's really, really central, is a rate of change. How much is something changing? How fast is it changing? Right? So we look for words like this: the rate of change, the instantaneous rate. How fast is something changing, or how slowly is something changing? If you see these, you know you're going to be using differentiation. A hint is that all of the questions in your exam, at some stage you will need to either differentiate or integrate, or both, but you'll need to do at least one. And if you see those, you're probably going to be differentiating. So you might be asking yourself, doesn't this have something to do with graphs? And yes, it does, but I don't want you to get too hung up on graphs. Graphs are just a visual way of showing a change in something. And really, when we talk about differentiation, we talk about slope and gradient. So in other words, if we have our xy axes here, and we have some function, say like that, this is getting steeper and steeper and steeper. So the gradient, the slope, is going to be getting greater and greater as x increases. Increases. That's that's terrible. Increases. That's better. You can read that. So as we go from left to right here, this line is getting steeper and steeper. And in fact, if we have a tangent is a straight line at a point. That's the same gradient as the function at that point. So here, the gradient at this point right here would be that. The tangent at this point here will look like kind of like that, just touching it and nothing else, but at the same gradient at that point. So tangent and gradient are linked. Tangent, let's define it, it's a straight line which just touches just touches the function at a point with the same gradient. Okay. So just as a refresher, if you have a slope that's like that, that's a negative slope. And a slope like that would be a positive slope. So imagine a little man walking from left to right. If he's walking uphill, it's positive. If he's walking downhill, it's negative. If it's flat, there is no slope. If there's a cliff, I guess there's infinite slope. But it's not really a gradient at all at that point. Next thing we want to be looking out for in questions is if it asks for a maximum or a minimum or a turning point, a stationary point, turning point, something like that. Best, worst, most, least, some extreme word like that. It's going to be, you're going to be using differentiation, and you're going to be applying certain tests to it. So if you remember, that would be a maxima point there because it's the maximum height, if you will. If you imagine this is a mountain, that's the sort of top of the mountain, and this would be a minima point here, the bottom of a valley. It's really, really important in a lot of functions to be able to work out exactly where that is. Previously, last year, you wouldn't have used calculus. You would have kind of used algebraic methods and sort of looked at them and kind of worked out where they are. Now it's exclusively using calculus, okay? And it is one of the most important things in calculus, especially in physics and especially in things like engineering and even chemistry. We really want to know the turning points there, and for economics and social studies as well. Okay, the next one is motion. How fast, how slow, what's the speed, what's the velocity, what's the change in the velocity. If something is not moving, that's when we would use differentiation. So if we imagine that we have a little car, you're going to have to put up with my terrible drawing. This is a maths class, not an art class, and it's going along the road there. It's changing its position, and the rate that it's changing its position is its velocity. And those of you who are doing physics, you'll know the difference between a velocity and a speed. A velocity can be negative, a speed can never be negative. How fast something is going. So if we know the function for where it is at any point in time, we can work out the velocity by differentiation. So in your car, when you want to change the velocity, you want to get faster, which pedal do you hit? You hit the accelerator. You hit the gas. Well, the hint is there. Acceleration is the change in velocity over time. If something gets faster, we say it accelerates. If something gets slower, we still say it's accelerating, but it has a negative acceleration in mathematics and physics. If something is decelerating, well, it means something a little bit different. By the way, to speed up, you hit the accelerator. to slow down, you don't hit the decelerator, you hit the brakes. Hopefully you hit the brakes before it's too late. But again, changes in how something is moving, changes in motion, whether something is in motion at all, we're going to be using differentiation to model that. So as soon as you see that, your little spidey sense should be saying, okay, we're going to be using differentiation. So at this point, I just want to take a little sidestep and just look at the notation, the way that we write differentiation. There's two ways of writing it. And again, if we see words like differentiate, you know that you're going to be differentiating it. If we have a function f of x and we differentiate it, we're going to write it like this. And sometimes you can see the f is sometimes written like that to show that it's a function. So it's going to be the same as before, but there's going to be like a little apostrophe there to show that it's differentiated. Okay, so this is the original function and this is the differentiated function. Okay, technically if you see it like that, that means that it's a differentiable function, that we can differentiate it. You'll see that there is a sort of a slightly different notation there. One is Leibniz notation, one is Newtonian notation. I always forget which one is which. I think that's Newtonian, that's Leibniz. Two guys invented calculus at the same time, and they use different notations. If we have the original function y equals, if we differentiate it, it's dy over dx, and treat that as one sort of function all by itself. It's not really a function, it's an operator really. And what that means is change in y over change in x. These are not entirely the same, but they're 99% the same. They mean the same thing, essentially. One thing I do want to say is, don't get in the habit of kind of this funky looking D, or that kind of looking D, or triangles, or something like that. Don't be using those if you can. Stick with D. These things actually mean something completely different in mathematics and calculus. This just means read this as change in y given a change in x. And you can kind of imagine it as the slope, as kind of the rise over the run in last year's terminology. Again, stick with D. If they give it to you in D, don't get fancy, don't try to be clever, stick with that. One that you may see though, having said that, you may see change in x over change in y. That means an observed change. Okay, so say you're timing something, and at time there, when we start off, it's at this position, and after such and such time, it's at this position. That's when you would use these symbols, but until then, don't use those. Stick with the dy over dx, but more preferably, actually, stick with this f of x, f dash of x. Okay, if we differentiate it again while I'm looking at it, so we have our original function here, and we differentiate it, and we get f dash of x. If we differentiate that again, which we will be doing a bit later on, it's going to be f dash dash of x. And I guess we could go on forever and ever, s dash 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 of x. It would get ridiculous after a while. You tend to use kind of like numbers like that, but you'll not need to use that at this stage. The most you'll ever need to do is differentiate something twice. And there's really good reason why you'd want to differentiate it twice, and we're going to get to that in the next lesson.